Picture a civilization so advanced that they don't just build cities or nations, they construct entire megastructures around stars, wrapping their sun in a vast, shimmering net of energy-harvesting technology. This isn't just science fiction, it's a real possibility lurking in the future of human ingenuity. Imagine a swarm of billions of solar collectors, each one orbiting a star like a colony of fireflies, working together to capture every last drop of its radiant power. This is the vision of a Dyson swarm, a feat of engineering so grand it would make our greatest modern achievements look like child's play. And what's even more astonishing, the energy harvested could unlock possibilities we've only dreamed of: interstellar travel, artificial worlds, even the power to reshape galaxies. But how close are we to making this a reality? The idea of a Dyson swarm springs from the mind of physicist Freeman Dyson, who imagined a civilization so advanced that it could harness the full output of its star. Think about that for a second. Our sun alone emits enough energy in 1 second to power human civilization for hundreds of thousands of years, if only we could catch it all. A Dyson swarm wouldn't just solve our energy needs, it would redefine what a civilization can become. We're talking about a species graduating from planetary inhabitants to galactic architects, wielding the power of stars themselves. Now here's the thrilling part: we might not be as far from this future as you'd think. Scientists and engineers are already sketching out the early steps, from self-replicating robots to space-based solar farms. The challenges are enormous, but the rewards, they're literally astronomical. So if you've ever stared up at the night sky and wondered what humanity's ultimate destiny might look like, buckle up. Because today, we're diving deep into the science, the possibilities, and the mind-bending implications of Dyson swarms, the megastructures that could turn us from earth-bound creatures into true lords of the cosmos. And trust me, by the end of this journey, you'll never look at a star the same way again. A Dyson swarm isn't just a single massive structure. It's a constellation of countless individual solar collectors, each one a carefully crafted satellite designed to orbit a star in perfect harmony. Picture this: a fleet of mirrors, solar panels, or even advanced energy converters, all dancing around a sun like a meticulously choreographed ballet. Their sole purpose: to capture and redirect the star's unimaginable energy output, transforming raw sunlight into usable power on a scale that dwarfs anything we've ever achieved on Earth. Unlike the classic concept of a solid Dyson sphere, a rigid shell completely enclosing a star, a swarm offers flexibility and practicality. It doesn't require materials strong enough to withstand the crushing forces of a star's gravity or the engineering nightmare of maintaining a single seamless structure. Instead, it's built piece by piece, a modular network that can grow over time, adapting as technology advances or energy needs expand. The brilliance of this design lies in its scalability. Imagine starting small, just a few dozen solar collectors launched into orbit. Over decades or centuries, that initial cluster could multiply into millions, then billions, each new addition feeding energy back to a central hub or distributing it across an interstellar civilization. Some theoretical designs even suggest using lightweight, self-replicating drones that could mine asteroids or planetary material to construct more of themselves, turning the swarm into a self-sustaining project. And unlike a solid sphere which would block starlight entirely, a swarm allows precise control over how much energy is harvested, leaving the option to beam sunlight to planetary surfaces or other installations as needed. But why go to such extremes? The answer lies in the sheer enormity of a star's energy. Even a fraction of our sun's output could power entire civilizations for millennia, fueling everything from massive supercomputers to continent-sized habitats. A Dyson swarm wouldn't just meet energy demands, it would open doors to technologies we can barely conceive of today. Think about quantum-scale manufacturing, interstellar propulsion, or even reshaping planetary climates with directed energy. This isn't just about sustainability, it's about unlocking the next evolutionary step for any civilization bold enough to reach for the stars. And while the challenges are daunting, from the physics of orbital mechanics to the politics of coordinating such a vast project, the swarm's modular nature offers a path forward. It's a slow, steady climb rather than an impossible leap. Every new satellite deployed, every innovation in material science or energy transmission, brings us closer to a future where humanity doesn't just live under sunlight, we command it. To harness the power of a star, we need to understand the physics behind star harvesting, and it all starts with light. Every second, our sun releases enough energy to power human civilization for over 500,000 years. A Dyson swarm captures this staggering output by deploying vast arrays of solar collectors, each converting sunlight into usable energy through advanced photovoltaics or even more exotic methods like thermal absorption. But here's the kicker: capturing the energy is only half the battle. The real challenge lies in transmitting it across space. Some proposals suggest beaming power via microwaves or lasers to receiving stations orbiting planets or deep space habitats, a method already being tested in small-scale prototypes today. Others imagine storing energy in portable batteries or antimatter reservoirs for interstellar travel. The materials needed for such an endeavor would have to be lightweight, durable, and capable of withstanding extreme temperatures. Think graphene, carbon nanotubes, or self-repairing metamaterials mined from asteroids. Where does this place us on the cosmic ladder of progress? Enter the Kardashev Scale, a framework that categorizes civilizations by their energy mastery. A Type I civilization uses all the energy available on its home planet, something humanity is inching toward. But a Type Roman II civilization, the tier where Dyson swarms come into play, operates on an entirely different level. This is a society that doesn't just consume the energy of a star, it commands it, bending sunlight to fuel everything from planet-sized megacities to faster-than-light propulsion experiments. Picture a culture where energy scarcity is a forgotten concept, where the limits of growth dissolve into the vastness of space. Reaching Type Roman II status would demand more than just technological leaps. It would require a fundamental shift in how we think about collaboration, resource allocation, and even time itself. Constructing a Dyson swarm wouldn't be a single generation's project. It could span centuries, even millennia, demanding long-term vision on a scale we've never attempted. And yet, the seeds of this future are already here. From breakthroughs in fusion reactors to the rise of space-based solar power, humanity is taking its first trembling steps toward the stars. The path won't be easy, but the destination, a civilization bathed in starlight, limited only by the boundaries of its ambition. Building a Dyson swarm isn't just about ambition, it's about redefining the limits of engineering itself. The first hurdle, scale. Enveloping a star with solar collectors means constructing billions, perhaps trillions, of individual units, each requiring precision deployment across millions of miles of space. Traditional construction methods won't cut it here. Instead, we'd need armies of autonomous, self-replicating robots, machines capable of mining raw materials from asteroids, refining them in zero gravity, and assembling new copies of themselves without human intervention. These wouldn't be the robots of today, clunky and limited, but sophisticated nanofactories, blending artificial intelligence with advanced manufacturing to turn space itself into a production line. Orbital mechanics adds another layer of complexity. Each collector must occupy a stable path around the star, avoiding collisions while maximizing energy capture. Some might orbit close to the sun, enduring blistering heat to absorb intense radiation, while others operate farther out where sunlight is weaker but materials last longer. Coordinating this celestial ballet would demand algorithms far beyond our current software, capable of predicting gravitational nudges from planets, solar flares, and even the swarm's own shifting mass. And let's not forget maintenance. These machines would need to repair themselves, share energy during eclipses, and adapt to decades of wear without human hands to fix them. Then there's the question of materials. Earth's resources couldn't possibly supply a project of this magnitude. Instead, we'd turn to the asteroid belt, where metals like iron and nickel float in abundance, or even mine Mercury for its rich deposits of silicon and titanium. Space-based manufacturing would become essential, leveraging the vacuum and microgravity to create alloys and solar cells impossible to forge on Earth. Imagine factories floating in the void, powered by the very sunlight they're built to harness, churning out solar panels as fast as a star's energy allows. The timeline, daunting. Even with exponential growth, each robot building 2 more and those building 4, the swarm would take centuries to reach full capacity. This isn't a project for impatient minds. It's the work of generations, a testament to humanity's ability to plan beyond lifetimes. Yet step by step, from the first prototype to a web of collectors stretching across the solar system, each milestone would bring us closer to a future where the energy of a star isn't just a distant glow, but a tool in our hands. The engineering may seem impossible today, but so did flight or the internet or landing on the moon until it wasn't. The true power of a Dyson swarm lies not just in what it can do, but in what it makes possible. Imagine a civilization unshackled from energy scarcity, where every industry, every experiment, every dream isn't constrained by the limits of a power grid, but fueled by the raw output of a star. This isn't just about turning sunlight into electricity, it's about unlocking doors we've barely dared to knock on. Take interstellar travel, for instance. The energy required to propel a ship between stars is staggering, far beyond what Earth's resources could ever provide. But with a Dyson swarm, suddenly those numbers become manageable. We could beam concentrated laser propulsion to spacecraft, accelerating them to a fraction of light speed without carrying heavy fuel. Or we might synthesize antimatter in orbital factories, creating the most potent fuel known to physics, all thanks to the swarm's endless energy surplus. Then there's the matter of space itself, not as a frontier but as a home. Picture vast orbital habitats, each one a self-contained world supporting millions. Without the need to ration energy, these structures could mimic Earth's ecosystems perfectly, with artificial suns powered by beamed starlight and climate systems fine-tuned to perfection. And that's just the beginning. With this much energy, we could terraform planets on a timeline that feels almost magical, melting Martian ice caps or sculpting Venus's atmosphere into something breathable, all by redirecting solar energy on a planetary scale. But perhaps the most profound benefit is the freedom to experiment. A Dyson swarm wouldn't just solve our problems, it would let us ask new questions. What if we could simulate entire universes in quantum computers just to test theories? What if we could build megastructures that bend space-time itself, like Alcubierre warp drives or artificial gravity wells? When energy is no object, the only limits are imagination and physics. And for civilizations wise enough to share this power, it could mean an era of collaboration, not competition. Imagine multiple species pooling their swarms, creating a network of stars fueling a galactic renaissance. Of course, this future isn't guaranteed, it's earned. The same energy that could lift civilizations could also weaponize asteroids or destabilize stars. But that's the weight of this opportunity. With the power of a star at our fingertips, every choice becomes monumental. The swarm isn't just a tool, it's a mirror reflecting what humanity, or any civilization, truly values when given the keys to the cosmos. And that might be the most electrifying benefit of all. Harnessing the power of a star doesn't just raise engineering challenges, it forces us to confront profound ethical questions. What gives any civilization, no matter how advanced, the right to reshape something as fundamental as a star? Imagine stumbling upon a distant solar system where another species has begun dismantling planets or redirecting sunlight, all to fuel their own expansion. Would we see them as pioneers or interlopers, tampering with cosmic real estate that in some sense belongs to no one, or perhaps to everyone? The universe might seem vast and empty, but the moment we start altering stars, we're playing with forces that could ripple across galaxies with consequences we can't yet predict. Then there's the matter of unintended damage. A Dyson swarm, even partially constructed, could cast shadows on orbiting planets, disrupting climates and ecosystems that might harbor life. We've seen how delicate Earth's balance is. A slight shift in solar radiation could trigger ice ages or scorching droughts. Now picture a civilization accidentally freezing a once vibrant world into silence, all in the name of progress. And what if we're not alone? Microbial life could exist in the subsurface oceans of moons like Europa or Enceladus. By mining these bodies for swarm materials, might we unknowingly erase the first faint whispers of alien biology? The ethical weight here is staggering. We'd be making choices not just for ourselves, but for life forms we may not even recognize as alive. But let's flip the perspective. If humanity doesn't pursue star harvesting, are we resigning ourselves to a stagnant future? Energy scarcity has driven wars, inequality, and suffering throughout history. A Dyson swarm could erase those limits, offering abundance on a scale that ends resource conflicts forever. Isn't there a moral imperative to reach for that future, especially if it means lifting billions out of poverty or preventing environmental collapse on Earth? The philosopher's dilemma emerges. Do we prioritize the sanctity of untouched celestial objects or the survival and flourishing of our own species? This isn't just theoretical. Right now, treaties like the Outer Space Treaty of 1967 forbid nations from claiming celestial bodies, but they're silent on megastructures or stellar engineering. As private companies and governments eye asteroid mining and space-based solar power, the legal and ethical frameworks are lagging far behind the technology. Should a single corporation or nation have the right to harness a star's energy, or should it be a collective project governed by something like a cosmic UN? The stakes couldn't be higher. Mismanagement could lead to a new era of interstellar inequality, where the energy-rich control the fate of those left in the dark. And then there's the ultimate question: what happens to the star itself? Stars aren't just light bulbs to be unscrewed. They're dynamic, living engines whose life cycles shape entire galaxies. Some theoretical designs suggest tapping a star's plasma directly, skimming material to extend its lifespan, or worse, accelerating its death to extract every last joule. Would that be any different from strip mining a forest or damming a river, just on a cosmic scale? The irony is haunting. In seeking to master the stars, we might end up treating them the same way we've treated Earth, as resources to be consumed rather than wonders to be preserved. Yet perhaps the most humbling thought is this: the universe doesn't care. Stars are born, flare, and die regardless of our actions. Ethics are human constructs, and the cosmos operates on scales beyond our moral frameworks. But that doesn't absolve us of responsibility. If we're to become a civilization worthy of such power, we'll need more than engineering genius. We'll need wisdom. The kind that asks not just can we, but should we, long before the first solar collector ever leaves the launch pad. Right now, humanity couldn't build a Dyson swarm if we pooled every resource on Earth. Not even close. Our most advanced space technologies today would look like stone tools compared to the orbital megascale engineering required. Consider the International Space Station, humanity's crowning achievement in space construction. It took over 30 nations, 2 decades, and $150 billion just to assemble a habitat the size of a football field. A single Dyson swarm satellite might dwarf that, and we'd need billions of them. The gap between what we can do and what this project demands isn't just large, it's cosmic. But let's break down exactly where we fall short. First, materials science. A solar collector orbiting close to the Sun would face temperatures hot enough to vaporize steel, cosmic radiation that shreds electronics, and micrometeorite impacts moving faster than bullets. We'd need revolutionary materials, think self-healing meta-alloys or carbon nanotubes woven at astronomical scales just to survive the environment. Then there's energy transmission. We can't even beam solar power efficiently from Earth orbit to the ground, yet last year's tests managed about 60% efficiency over a few hundred miles. Scaling that to interstellar distances while minimizing energy loss would require breakthroughs in laser physics we've only theorized about. Manufacturing is another roadblock. Today's factories can't produce spacecraft fast enough to matter. It takes SpaceX months to build a single Falcon rocket. A viable swarm would need autonomous orbital factories churning out thousands of satellites per hour, likely using self-replicating machines that clone themselves from asteroid materials. And that's assuming we solve the AI control problem, creating robots smart enough to build without human oversight, but disciplined enough not to turn the solar system into paperclips. Yet for every show-stopping challenge, there are glimmers of progress. Private companies already test 3D printing in zero gravity, hinting at future orbital factories. NASA's DART mission proved we can redirect asteroids' potential mining sites for swarm materials. Breakthroughs in quantum computing could one day model the swarm's complex orbital dances. Even fusion research, though earthbound, teaches us about manipulating stellar energies, the critical missing piece, scale coordination. No single nation or corporation could fund this. It would demand unprecedented global cooperation spanning centuries. Imagine a modern-day Apollo program multiplied by 1,000, where generations of engineers hand off blueprints like relay batons. The timeline alone boggles the mind. Construction might take longer than all recorded human history so far. But here's what's thrilling. We're already laying groundwork without realizing it. Every solar panel bolted to a rooftop, every asteroid prospecting startup, every test of wireless power transmission brings us incrementally closer. The path to a Dyson swarm isn't a sudden leap, it's 1,000 small steps we're already taking. What feels impossible today might simply be waiting for the right sequence of discoveries, like 15th century sailors imagining continents they couldn't yet reach, unaware their grandchildren would walk those shores. A Dyson swarm might be the most famous idea for harvesting a star's energy, but it's far from the only option. Picture a solid Dyson sphere, the classic sci-fi megastructure, a single, seamless shell completely enclosing a star like a giant light bulb. Theoretically, it could capture nearly 100% of the star's output, with none of the energy escaping into space. But here's the catch: building something like that is a nightmare of physics and engineering. The gravitational forces alone would be staggering, pulling equally from all sides, requiring materials stronger than anything we know of to avoid collapsing inward. And what about heat? A sealed sphere would trap radiation, cooking itself unless it had some way to vent excess energy, an engineering puzzle we're nowhere close to solving. That's why a swarm of smaller, independent satellites is far more practical, even if it sacrifices some efficiency. Then there's the stellar engine, a megastructure designed not just to harvest energy, but to move an entire star. The most famous design, the Kardashev thruster, works like a giant parabolic mirror, reflecting a portion of the star's light to create thrust. Over millions of years, it could steer a solar system across the galaxy, avoiding cosmic hazards or even relocating to richer interstellar neighborhoods. But the trade-off, it's slow, requiring patience on timescales beyond human comprehension, and it leaves most of the star's energy untapped. A hybrid approach might combine a Dyson swarm with a Kardashev engine, using some satellites for energy collection while others focus on propulsion. Black hole batteries offer an even wilder alternative. Instead of harnessing stars, a civilization could feed matter into a small, artificial black hole, capturing the intense radiation it emits as it devours material. The energy output could dwarf even a star's, with efficiency nearing 40%, far better than nuclear fusion. But the risks are terrifying. A miscalculation could let the black hole grow out of control, swallowing everything around it. And creating one in the first place would demand technology we can't even fathom, like compressing matter to densities beyond neutron stars. Each of these megastructures presents a different vision of the future, some practical, some speculative, all stretching the limits of what we believe is possible. The choice between them isn't just about engineering, it's about what kind of civilization we want to become. Do we prioritize stability and gradual growth like a Dyson swarm? Chase the dream of galactic travel with a stellar engine, or gamble on the extreme energies of black holes, betting that we can tame the most destructive forces in the universe? These aren't just technical decisions, they're philosophical ones, revealing what we value most when the stars themselves become tools in our hands. Astronomers hunting for alien megastructures face a cosmic needle in a haystack challenge, except the haystack is the Milky Way, and the needles might be hiding in plain sight. The key lies in starlight itself. When a civilization builds a Dyson swarm, it inevitably alters the way its star shines. Imagine a star that flickers unpredictably, dimming by irregular percentages at uneven intervals, as if something enormous and artificial were passing in front of it. That's exactly what astronomers observed with Tabby's star, a mysterious object in the constellation Cygnus that made headlines for its bizarre behavior. Unlike ordinary stars, which dim rhythmically due to orbiting planets or natural dust clouds, Tabby's star faded by up to 22% in chaotic dips, far too extreme for any known astronomical explanation. Could this be the signature of a vast, incomplete Dyson swarm under construction? The idea electrified the scientific community, though later studies suggested less exotic causes, like swarms of comets or interstellar debris. But the tantalizing possibility remains. If we find enough stars behaving strangely, we might just stumble upon evidence that we're not alone. The search doesn't stop at odd dimming patterns. Advanced civilizations might leak infrared radiation, a telltale byproduct of energy collection. Here's why: a Dyson swarm absorbing sunlight would eventually irradiate the energy as waste heat, glowing faintly in the infrared spectrum. Telescopes like NASA's WISE mission have scanned millions of stars for this exact signal, flagging candidates with unexplained infrared excesses. One standout: a star labeled WISE 08002 plus 2684, emitting 94% of its light as infrared, a ratio so lopsided it defies natural explanations. While dusty debris disks could mimic this effect, the extreme findings keep astrophysicists debating. The challenge is separating cosmic anomalies from potential engineering projects. After all, nature doesn't always play by neat, predictable rules. But what if alien swarms aren't just passive collectors? A civilization manipulating starlight might deliberately broadcast its presence. Picture a Dyson swarm designed to flicker like a lighthouse, pulsing energy in coded patterns across the galaxy. Such technosignatures would stand out against the steady rhythm of natural stars, acting as a cosmic handshake. Projects like SETI have expanded beyond radio waves to scan for exactly these kinds of engineered signals in starlight itself. The beauty of this approach: unlike radio transmissions, which fade over interstellar distances, a star's modified light could be detectable across thousands of light years. Of course, every potential discovery comes with caveats. The universe is vast, and rare phenomena often masquerade as intelligence. A shattered planet, a dense asteroid field, or even a chance alignment of cosmic dust can mimic a Dyson swarm's fingerprints. That's why astronomers cross-examine each candidate with multiple instruments, ruling out natural explanations one by one. The hunt isn't about jumping to conclusions, It's about eliminating the impossible until whatever remains, however improbable, demands a closer look. And that's the thrilling part. Even if today's oddballs like Tabby's star turn out to be natural, they've proven our methods work. Every peculiar dataset refines the search, sharpening our tools for the next candidate. With next-generation telescopes like the James Webb or the upcoming Vera Rubin Observatory, set to map billions of stars in unprecedented detail, the odds of spotting something truly inexplicable are rising. Whether we find alien megastructures or not, the search itself rewrites our understanding of the cosmos, proving that sometimes the most profound discoveries begin with a single, flickering point of light in the dark. Once a civilization masters the energy of a single star, the next leap is almost inevitable, scaling up to galactic proportions. Picture a type Roman III civilization on the Kardashev scale, one that doesn't just harness a sun, but taps the combined power of billions of stars across an entire galaxy. This isn't just about expansion, it's about reinventing the rules of existence. Imagine networks of Dyson swarms linked by faster-than-light communication, forming an interstellar energy grid where surplus power from young, blazing stars is routed to older systems or transported to galactic construction sites. The scale is mind-bending, entire nebulae reshaped into power plants, pulsars engineered as natural batteries, or even dormant black holes awakened as cosmic generators. But why stop there? Black hole farming could become the ultimate energy hack. A single rotating black hole, fed carefully controlled streams of matter, could emit colossal amounts of Hawking radiation, a theoretical energy source far more potent than starlight. Advanced civilizations might cultivate these cosmic anomalies like crops, seeding them in sterile regions of space to avoid catastrophic accidents. The math is staggering. A black hole the mass of a small moon could output petabytes of energy per second, lasting for millennia before evaporating. And for the truly ambitious, there's the possibility of crafting artificial stars, compact fusion reactors scaled to celestial proportions, lit on demand and extinguished when their work is done. These wouldn't be natural phenomena, but precision tools ignited in the void to power megaprojects or even serve as beacons for intergalactic travel. Then there's the darker, more speculative edge of cosmic engineering, star lifting. Instead of merely collecting a star's energy, a hyper-advanced civilization might siphon off its plasma directly, extending the star's lifespan while mining it for heavy elements. Think of it as stellar surgery, carefully removing layers of hydrogen to slow fusion rates, turning a short-lived giant into a stable, long-term resource. The extracted material could fuel everything from giant quantum computers to self-repairing megastructures, but the risks are equally cosmic. Miscalculations could trigger supernova or accidentally create black holes, turning a power source into an existential threat. The strangest possibility, a civilization that outgrows stars altogether. Beyond type Roman III lies the realm of post-stellar societies, where energy isn't drawn from fusion but from the fabric of spacetime itself. Quantum vacuum energy, zero-point fluctuations, or even the manipulation of dark matter could render stars obsolete. In this distant epoch, galaxies might appear dim to outside observers, not because they're dying, but because their inhabitants have moved beyond light, harvesting energy from dimensions we can't yet perceive. The common thread in all these scenarios isn't just raw power, it's the reimagining of the universe as something malleable. A Dyson swarm is just the first stitch in a tapestry of engineering that could one day weave together galaxies. Whether through black holes, artificial suns, or technologies we haven't yet named, the far future belongs to those who see the cosmos not as a static backdrop, but as raw material waiting to be shaped. And that might be the most profound shift of all, not just in how we power our machines, but in how we define what's possible. What we've explored today isn't just science fiction, it's a roadmap to humanity's potential destiny among the stars. Dyson swarms represent more than an engineering marvel. They're a gateway to civilizations that operate on cosmic scales, turning starlight into the lifeblood of progress. Think about it. Every sunrise we take for granted here on Earth is a fraction of the raw power waiting to be unlocked. With that energy, we could rewrite the rules of scarcity, explore the galaxy without limits, and even reshape worlds to our needs. The magnitude of that possibility is humbling, not just for what it says about technology, but for what it reveals about us. Are we a species content to orbit a single star, or are we destined to become architects of the universe itself? Here's the breathtaking part. The science behind this vision is already taking shape. From early experiments in space-based solar power to the first tentative steps toward asteroid mining, humanity is laying the groundwork for a future that might once have seemed impossible. The challenges are immense, but so is the payoff. A single Dyson swarm could fuel millennia of discovery, from cities floating in the void to engines that bend space-time. And if other civilizations have already achieved this, the universe might be teeming with starlight harvesting societies, their presence hidden in the flicker of distant suns. So let's end with a question that lingers long after this video fades to black. If humanity had the power to harness a star, would we use it to light a beacon of collaboration or a weapon of conquest? The answer might define not just our future, but the future of every civilization that follows. Drop your thoughts in the comments below. Are we on the brink of becoming galactic engineers, or is the cosmos better off without us tampering with its stars? The conversation starts now, and who knows, the next great idea might come from you.